Hi everyone, my name is Kevin Bach from the University of Maryland, and today I'm going to be talking about a brand new form of amplification attack that for the first time works over TCP. Before I get into that though, I want to give a brief run through of how amplification attacks work. Now the goal of this attack is for some attacker to flood and overwhelm the bandwidth of a victim to make them unavailable. A powerful tool in the arsenal of such an attacker is that of a reflected amplification attack, and an attacker does this by using an open server to assist with the attack. The attacker pretends to be their victim by spoofing their IP address, sends a request to this open server, which then dutifully responds to the victim, and ideally for the attacker with a response that was much larger than the request. We can quantify the amplification factor for the attacker as the size of the response they can elicit divided by the size of the request. And historically, there have been some very large attacks like this: DNS, NTP, Memcached, just to name a few. But the thing is that almost all of these attacks have historically been limited to UDP. And the reason for this is that UDP is a connectionless protocol. There's no setup needed before a client and server can start communicating. So it's amenable to this idea of pretending to be your victim, making a request, and then just letting that server send a large response to your victim. TCP, on the other hand, has been spared for most amplification attacks. And the reason for this is that TCP requires a three-way handshake. This is an exchange of information between the client and server that they'll use when they make the real request. What this means is that if an attacker tries to do a three-way handshake while pretending to be their victim, when they start this exchange, the server's response goes to the victim. So the attacker is missing that critical bit of information they need to complete the handshake. And of course, even if they try and complete the handshake anyway, the information will be incorrect. The server knows this and will shut down this connection. This means that the attacker is unable to use the server to issue requests and get amplification. Now, technically, there is some small amplification offered by retransmitted syntax during this initial exchange. And this is how TCP has been used in the past to launch these attacks. But the actual request and response, the meat of this exchange, has always been believed to be off limits to attackers until today. In this presentation, we're going to show that TCP-based amplification is not only possible, it can also be startlingly effective. We're going to present on 5 distinct attacks that make this possible. I'll show how we found millions of IP addresses that can act as amplifiers, and discuss the enormous amplification factor we discovered. And in some cases, we actually found infinite amplification. The insight that enabled this work is that networks have grown more complicated since we last reasoned about TCP amplification, and we can use Middleboxes themselves as amplifiers. So let's walk through how this works. Nowadays, if an attacker sends packets to some open server, there's often more hosts on the path. There can be a Middlebox there, and these take many forms: firewalls, IDS or IPS, or in many cases, nation-state censorship infrastructure. And there are a few properties of these Middleboxes that make them good targets for this attack. First, Middleboxes expect to miss some packets. There could be asymmetric routes, routes that change, load balancing, etc. So for example, if this Middlebox sees a request for pornography without seeing a three-way handshake, the Middlebox must just often assume that it missed it. Because after all, why else would a client send a perfectly well-formed request for pornography without a three-way handshake? The second aspect of these Middleboxes is that they commonly inject traffic when they want to block a connection. They start by spoofing a destination, and they can inject traffic, and this includes reset packets or large block pages. Worse for the victim, this traffic appears to come from the original destination, not from the Middlebox itself. In a sense, Middleboxes essentially get rid of the challenges posed by traditional reflected TCP attacks by not requiring the three-way handshake properly and reflecting the response to the victim. This leads us with 2 questions. First, what is the best way to trigger these Middleboxes? And as we'll see, it's not often enough just to send the request. You often need to do a little bit more work than that. And second, what kinds of amplification factors can this attack give us? So to answer this question, our methodology consisted of 2 broad stages. First, we needed a way to automatically discover ways to trigger responses from these Middleboxes. Remember, we're taking advantage of flaws in TCP implementation, not in the protocol design of TCP itself. So we can't study the protocol. We need to study real implementation of TCP in these Middleboxes. To tackle this, we made use of a tool called Geneva. This is a learning genetic algorithm we originally designed to evade censorship, but it's effectively a network fuzzer. And we changed its fitness function to reward it for finding ways to elicit large amplification factors from Middleboxes. So we trained Geneva 184 times on censoring Middleboxes around the world identified by censored planet. And this will give us the output is a series of packet sequences that can elicit responses from Middleboxes. Then we scanned the entire IPv4 internet, actually a total of 35 times, to identify just how much amplification factor we could get. Also important to note here that we did also responsibly disclose our findings. We reached out to many country-level certs, DDoS protection services, and Middlebox manufacturers. So what did we find? In general, Geneva found a few broad ways to elicit responses. You can send a SYN packet containing a well-formed HTTP request for forbidden content. You could directly make that well-formed request, again, with no proper three-way handshake, or to send a SYN packet, follow it up with the real request. And we found this request could be sent on either a push or push-ACK packet. So in total, we found 5 total packet sequences. And you notice here that in all these cases, we're not doing the three-way handshake properly, or we're completely butchering it. And Middleboxes can still be triggered without any ACK packets whatsoever. Detailed in the paper, we also find a number of tiny variants, which can be used to improve amplification for a small number of Middleboxes. They don't work globally, but for targeted attacks, they can also be used to improve things. Now recall that not only do we need to send a sequence of packets that a Middlebox will process and think is a real connection, it also needs to be content of the Middlebox forbids that makes it respond. So we analyzed Censored Planets data and found these 5 domains as eliciting responses from the most number of Middleboxes in the world. And this actually coincidentally spans 5 diverse areas: porn, gambling, social media, file sharing, and sexual health. And you'll see that here that Middleboxes differ in both their bugs and their configurations. So because of this, what amplification factor do we get when we bring this to the full internet, the IPv4 internet? This plot will show the amplification factor we get from all the IP addresses in the IPv4 space when they're sent this sequence of packets sorted by amplification. So this means that on the x-axis, all the way on the left is the destination IP address that sent the highest amplification, and all the way at the right is the lowest. And these are the 5 sequence of packets we sent. So first, you'll see the amount of amplification factor we can get is surprisingly high. Just look at the y-axis on this graph. There are hundreds of thousands of IP addresses with dangerously high amplification factors, and hundreds of millions more that can act as weak amplifiers. But the packet sequence we send also affects the amount of amplification and the number of IP addresses that respond. Now I'll draw special attention here to 2 parts of this graph. The first is the tall head of this graph, where you see these crazy amplification numbers like 10 to the 8, 10 to the 6, etc. I'm going to defer this and speak to this more in a minute. The second thing I want to discuss is this long tail of this graph. And we find that this is caused by nation-state censors. These are censoring Middleboxes with relatively low amplification factors, but with millions to hundreds of millions of IP addresses behind them that effectively act as weak amplifiers. We also organized and studied this by triggering domain. What do we get when we send for each of these domains? Now you'll see once again that many of these still elicits enormous amplification. The choice of domain affects the amount of amplification we can get. You'll see most of them still trigger a huge number of IP addresses, and all of them do considerably better than the control scan in blue, in which we sent no domain whatsoever. But overall, this raises an interesting question. Because different Middleboxes require different things to trigger them, how well could a perfectly informed attacker do that knew exactly what to send to every Middlebox? This graph shows what that perfectly informed attacker would be able to do with today's IPv4 internet. You can see exactly how many amplifiers we find that elicit each amplification. For example, here, this is over 300,000 IP addresses with greater than 100x amplification. So this attack is very powerful. You can also see how many IP addresses then exceed the UDP amplification numbers for DNS, NTP, and Memcached. And overall, this shows that TCP-based amplification is at least as powerful as its UDP-based alternatives. Now I want to discuss the head of this graph, where you see this truly mind-boggling amplification numbers on the y-axis. We call these mega amplifiers, and the amplification factor on the y-axis here is actually an underestimate. This is not when these IP addresses stop sending data. It's when we stopped recording traffic. And in some of these cases, these IP addresses continued to send us traffic indefinitely, effectively offering infinite amplification. For the remainder of this talk, I want to walk through how that happens. First, the first cause we find here is victim-sustained loops. So after an attacker triggers a Middlebox to amplify its traffic, Middlebox sends that data to the victim. But of course, the victim isn't expecting this data. And the proper client behavior for most TCP stacks when they see data they don't expect is to send a reset packet back to the destination. We found, though, that some Middleboxes are overly sensitive to seeing any packet from either side of the connection. And in fact, any packet at all will cause that Middlebox to re-trigger censorship and resend another block page to the victim. This, of course, then causes the victim to send another reset, which causes another block page to be sent by the middle box, and this continues indefinitely. This victim-sustained amplification is effectively infinite. This attacks both the victim's uplink and their downlink. The second cause for this is we can see this by looking at what really happens when an attacker sends data to the open server. Because what's really happening is it's going through a series of routers. And sometimes there could be a misconfiguration, and this misconfiguration can cause a routing loop. Now, for traditional amplification, this would stop things right there. This would mean that the attack packet would never reach the amplifier. When an attacker weaponizes a middle box, every time that offending packet loops past the middle box, it re-triggers that middle box, resulting in repeated triggering of the middle box every time that packet circuits the routing loop. This effectively makes the attack even more powerful than it was previously. Finite routing loops offer greater amplification the higher the TTL value you provide. So this is in effect offers an attacker a free increase in amplification by 240 to 250 times their previous amplification factor. And on top of that, we found a small number of infinite routing loops that traverse censorship infrastructure. And we found this in a number of countries, most notably in China and in multiple ISPs in Russia. Now, there are many other details and results in the paper that I don't have time to talk through today. We analyzed fingerprints from the packets we got from middle boxes. We did experiments to confirm that the data we're seeing is in fact from middle boxes and not just weird end hosts. We did a detailed analysis of the routing loops we saw, did an analysis of the impact of national firewalls and more. In summary, here we presented a new TCP-based amplification attacks enabled by middle boxes. These middle boxes are all over the world, and we found ways to automatically discover how to launch these amplification attacks. If you want to check out more, please see our code and website at censorship.ai, and I'm happy to take questions after this talk. Thank you.